Example is given by from fluid mechanics. If we have a two-dimensional flow given in x and t, at any point we have the velocity field v, which is given by which has component u and v. If the flow is incompressible, if v is incompressible, which means that divergence of v is equal to 0, I can express v as the gradient of a stream function wedge product with the vector z. And this means what? This means ijk of the phi dx, the psi dy, 0. Then we have 0, 0, 1. So then we have what? We have the high component is gonna be equal to this determinant, so the psi dy, this times this. Then we have minus j, I have plus the psi dx, plus k, basically 0, okay? So I can define this is gonna be u, and this is gonna be v. So the velocity field v can be written as plus the stream function y and minus the derivative of the stream function with respect to x. So psi is the stream function. And you can clearly see that the divergence of v is automatically 0, because the ddx of the psi dy plus the dy of minus psi dx, and this is equal to 0. Actually, we can reformulate this problem in terms of stream functions, because in the domain x and y, if this is the velocity field v, the velocity field v is also equal to the Lagrangian velocities dx dt, dy dt. But this is going to be equal to what? To plus the psi dy minus the psi dx. And here we have the stream function is a function of x and y. So we derive that dx dt equal plus the psi dy and dy dt equal minus the psi dx. And this can be reformulated as a Poisson bracket, because phi is as a Hamiltonian system, because the stream function is basically the Hamiltonian. Okay, you can clearly see the equations. Actually, no, to be precise, no, the true notation is going to be dy dt equal minus the psi dx and dx dt equal plus psi dy. And phi is the Hamiltonian, and that is easy to see, because if we derive the dynamics of any observable, df dt is equal to df dt plus df with respect to x, dx dt plus df dy dt. And this is equal to this, and then this is equal to this. Is right? So we have this and we have that. So I can rewrite this guy as equal df dt plus df dx dip c dy minus df dy dip c dx. And here I have now the famous brackets equal df dt plus f comma h comma c. Okay, so here we have the same brackets, f comma h equal df dx dip c dy minus df dy dip c dx, and these are the Poisson brackets, the one that we already got before. Okay, so you can see that in this case, the Hamiltonian has nothing to do with the kinetic energy of the system, of the velocity field, or the total energy. It is simply related to the stream function, and the evolution is this flow. It is in such a way that as the flow evolves, the stream function stays constant. Okay, which, I mean, we know that the particle the particle trajectories, the fluid trajectories, the fluid particle trajectory, they lie basically on these surfaces given by the constancy of the stream function. Okay, this and the second part of the